Now we're going to get into the actual weighing part of it. So we know we've talked about what the different weights can be, why we need to know it. We'll get into the calculations a little bit more detailed here in a minute. But how do we weigh an aircraft? So there's three main ways, or it can be a combination. The first is axle jacks, which are not shown here, but underneath this gear, or you've seen the jack point, you had to identify the jack point on the 727 gear. You can put a load cell underneath between an axle jack and that jack point. The wheels themselves, here we are onto a pair of platform scales, and that's what we're going to use for our aircraft here. We have floor scales that you'll use. The third one is a jack point, and so here you have a jack, and this thing in yellow kind of looks like a Lego head, right? I'm going to play Lego, the little heads. That's a load cell. So you can see the wire coming out of it, and this is a cool one. It's remote. You don't have wires. The ones we had wires running everywhere, and they turned into a big spaghetti cable nasty mess. And it took longer to sort them out than it did to set them up and actually do it. But the load cell, at points, various points, you can take that weight and add it up. You can also take the weight at the different points, those jack points or those gear or those axle jacks. They have an arm in relation to the datum, and so you can not only calculate the weight, but the CG of the aircraft. And sometimes you have a combination as well, although most of the time you're using the same types for all three. There's usually three waypoints, but you can, in some cases, use a combination, say two main axle jacks and a nose fuselage jack point, something like that. This jack point right here, by the way, really makes me nervous. Just doesn't seem like it's at the right angle, but that's how it looks. That is an actual, I think it's an Airbus, if I remember right. So how do we do this? So a very, very simple CG calculation is, at minimum, we have to have two, right? We have to have two different points in order to calculate the center of gravity between those 2 points. Hopefully it's between the 2 points. So we have a minimum of two scales on aircraft because they tend to be viewed from above, fairly triangular in nature. We have oftentimes three jack points, but two of them are in line with each other. The two wing points are almost always in line with one another. And so left-hand and right-hand main landing gear or wings make up the rear point. The nose, which can be fuselage or nose landing gear, or some aircraft, instead of the nose, they're going to be a tail. They have they're a tail heavy setup where you put the scale, the third scale, onto the tail. The aircraft has to be level so that weight is spread evenly, because the idea is that the plane should be pretty much level in flight. Okay. And to find our total weight, that's simple. We just add them together. So here, if we had two scales, a nose or a front scale, and say a wing scale, main landing gear, we have 650 pounds. Okay, so total weight, just add the scales together. And most of your scales, like that one we saw, or the one we'll use in class, you plug three scales in simultaneously, and it gives you the weight on this scale, and the weight on the second scale, and the weight on the third scale, and then it also gives you a readout for the total. It adds them for you. And then we have to use the arm position of the scales relative to the datum. Okay, so my example here, I just drew a datum, and we're going to say this front scale is 20 inches back from the datum. So is this a positive or a negative arm? Positive, because it's behind the datum. Okay, and then we'll call that main landing gear at 400 pounds, is 120 inches after the datum, so also a positive arm. And so we calculate the moment for each one. So the forward one, 20 times 250 gives us 5,000 inch-pounds, okay? Pound inches. 120 times 400 gives us 48,000 pound inches. Okay. And we combine those to get the CG. So the way we do that is we add our two moments together, 5,000 plus 48,000, and we divide it by the total weight of 650, gives us a CG of 81.5 inches. So if we lifted this beam up at that point, in theory, it would balance. It would be a balanced teeter-totter. It's kind of like you got the big kid on one side of the teeter-totter and the little kid on the other. Well, normally they don't balance, but if you had a teeter-totter where the little kid could sit further away, you could make them balance. And that's what we got going on here. That's a really big couple of kids, though. So the two primary types that we'll see in industry are our scales where we roll onto the platform and our load cells. And load cells are used between the top of a jack and the jack point. In this case, it's a removable jack point. You can see this red-orange piece here screws into the fuselage. On our King Air, it has jack points. They're fixed. You'll see these little nubby things sticking out when you do like gear stuff on it. But under normal operation, the jack just contacts that directly. When you're weighing it, you put this load cell between the top of the jack and these are extremely sensitive. The ones we had would go to about half a pound. And when you're lifting an airplane that's total of 60,000, 80,000, 100,000 pounds, a half a pound is pretty precise, right, for one of these cells. We have to subtract out that tare weight. We talked about it earlier when we looked at the excuse me, when we looked at the weight and balance record and the pilot operating handbook, where we subtracted out the chocks in that case. But items that may have to be taken out, support equipment used during jacking, so the jack pads, that's that, in the case of this, it's that orange thing that's screwed into the side of the fuselage. You'll know how much those weigh. You have to subtract that out. Jacks themselves, sometimes the way the jack is configured, a portion of the jack weight is included. Any kind of balance weights. So, is it the Baron? You have to put the tail weights on it when you're doing weight and balance, something like that. We haven't done the Baron, but it's got kind of a... Yeah, there's some airplanes where you actually, you lift it at the wings, and instead of lifting the nose, you put a bunch of weight on the tail and like teeter-totter it on the mains. It's kind of a goofy setup. And so you would have to subtract those balance weights. Chocks, gear pins, when we'd weigh them, bigger airplanes, you can pin the gear in the down and lock position, and you would have to remove those. Sandbags, ballast bags, etc. So they have to be subtracted at the end, both out of the weight, and you have to go through the process of subtracting from the CG. And it's not a straight process of CG of those, CG of the airplane minus CG of those. You cannot add or subtract CGs. You cannot add or subtract the moment arm. Okay? You can add and subtract weights. You can add and subtract the arms. You cannot add and subtract moments directly. The leveling, we talked about different areas, whether you use a Spirit level, which also includes your digital type level. Spirit level is a bubble or a digital level. And then plumb bobs and leveling plates like we've seen on the 727. And then we get to that engine oil discussion. Do we include it or do we not? So remember, before 1978, Civil Air Regulations, Part 3, engine oil would not be included. If your engine oil is full, you can subtract it out, because typically you know the CG and you know the volume of oil. Or you can drain the engine. Your choice. It's probably easier just to fill it full and subtract it out. Newer aircraft since 1978, full oil is included. Most of the time you're going to top it off to the full mark, and that's where you're going to have it when you do your weight and balance. If for some reason you have a totally empty engine, then you would need to add that weight of the oil back in, and you would need to make the calculations to adjust the CG based on that oil being added back in. There's additional information in 4313B, 1B, Chapter 10, and in the TCDS. So other fluids, fuel is only the residual fuels included. Okay, that's unusable, undrainable fuel. Okay. What if there's fuel on board the aircraft? What do? Subtract the number. Do you know exactly where the CG and the weight of the fuel is? So one option is to drain it. What's another potential option? Burn it. Go out and run. Run, baby, run. What else? You could potentially fill it full. Now, the one thing you have to be careful of is you could fill it full and then subtract it. It would be a tare weight and a tare that you have to do. The one thing to be careful of is airliners. Oftentimes, you cannot put them on jacks with full fuel. Every airliner I worked on, you could, if they had more than a certain amount of fuel in them, you could not put them on jacks. It caused too much structural stress to the airframe, and so you had to be below a certain amount of fuel. The really nice part about airliners is they have extremely accurate fuel systems that tell you the weight, and then the manufacturers are really cool about giving you tables that say if there's this much fuel in this tank, this is what the CG is. So they'll give you all that information. But for the most part, usually what we would do is we would use a defueling truck to suck them as dry as possible, and then we would sump the fuel. We would have to sump as much fuel as we could sump out. Any remaining residual fuel, that would just be included with the weight. Hydraulic fluid, system and reservoir at normal full. Other liquids for aircraft operation, those would be full. That's not things like galley water or potable water or lavatory service. Those are not part of the norm. These are the things you need to do for the systems to run on the aircraft. Hydraulic fluid full, engine oil full, fuel would be empty, struts would be serviced, right? You'd have fluid in your struts. So those kind of things would be full. No drinking water, no lavatory pre-charge, that's your blue juice. If you have an aircraft with water injection, the water injection system would be empty, would need to be empty. You'd remove things like magazines, galley service, et cetera, et cetera. What about passenger service cards? What about, passenger safety cards, briefing cards? How would you handle those? You know the one I'm talking about? You open it up, it shows you what to do in the event of a fire, a water landing, and you know how to brace yourself and how to use the little inflatey life jackets. What do? You keep them on? You call them a tare weight? I'll ask this question. Are those required to be on the aircraft for safety purposes? Would that fall under required equipment? Would it be included in the empty weight? Yes, they are required equipment that have a location. There's supposed to be one in each seat back pocket. So we would have to go through and make sure there's one safety briefing card in every single pocket. Okay, they are considered operational equipment, safety equipment that has to be on the aircraft. Now you go in and you find like 5 in this pocket, and you find 1 in this pocket, and you find none in this entire row because for some reason people treat them like trading cards and hand them around. I don't understand. Like, most people don't even look at them, but yet they move. Passengers are a pain if you haven't figured it out yet. They do dumb things. Okay. So back to our 182. So this one was certified in 1971. It was built in 1974. That means it was prior to 1978. So we would treat this as a Car 3 aircraft. So what do we have to do with oil when we do weight and balance on our 182? You need to drain it, or you have to subtract it. Drain or subtract. It's not part of your empty weight. The other thing is this aircraft has 30 pounds of unusable fuel. We do include unusable fuel. That's that low spot in the bottom of the tank where we can't pull the fuel from. Okay? That is included. Okay? So if you have a totally dry tank, you would have to add that back in. Most of the time, if you empty the tank, you don't have a way to get that out unless you like pick the airplane up and dump it out or something. Or you sit there and like suck it out with a fluid transfer. So certificate of empty weight must include unusable fuel, 30 pounds at 46 inches, right? They give you a weight and an arm. I should go back. In this case, they say undrainable oil of 0. Now, that's it. Any undrainable oil would be included in the weight. But on this aircraft, you can drain all the oil. And so you would remove the full weight of the oil. And here they give you I don't think they give it to you here. It's on another spot further down. So we do include our unusable fuel. So if we look at a 182R, a later serial number that was built in 1983, I'm partial to things built in 1983. It'll be after 1978. It'll be 14 CFR Part 23, okay? And so here it says the certified empty weight must include unusable fuel and oil of 16.9 pounds, right? That's the full oil. Okay? So that's a plane built after 1978. So the easiest way to do that, fill it to the full mark before you weigh. If you have oil somewhere between empty and full, it's really, really hard to figure out the weight, and it's even harder to figure out what the CG of that oil is. Because again, you might have a sloped oil pan, or it might taper in, or might taper out, right? So it's really hard to figure out where that is. And then you do include that 24 pounds of unusable fuel in this case. So how do we calculate this? Once we have these weights, we have to do something with them. So weights we can add and subtract. To get the CG, there's two primary methods. I'm partial to the second method. You draw your own conclusion as we go along. So the first is empty weight CG formulas. And these are fun because there's different formulas for different aircraft styles. There's 4 of them. Or we can use a table. For the table, it doesn't matter what style aircraft you're using. Okay. So the 4 formulas for our 4 cases: a nose wheel tricycle gear aircraft can have a datum forward of the main wheels, or it can have a datum aft of the main wheels. And a tail wheel, tail dragger, or sometimes, what's the other name for a tail wheel aircraft that screws everybody up? It's a conventional gear aircraft, even though we don't see them as often today, right? They were the first type of airplanes. Datum forward of the main wheels, datum aft, okay? So those 4. You don't need you can write your equations down. This is directly copied a page out of the 4313, chapter 10. 4313, 1B, chapter 10. Covers weight and balance. So if you have your 4313, it's in there. If you have your mechanics handbook, these equations are in there. The variables, CG, that's what we're trying to figure out. Positives behind the datum. Negative is in front of. The W is the total weight. D is the horizontal distance, and this is where people really get screwed up. The horizontal distance from the datum to a main wheel weighing point. Not an arm, always positive. Okay? Even if the main wheels, like in a tail dragger, conventional, if the main gear are in front of the datum, when you're making that measurement, it would be a negative arm. It is a positive distance D. Okay? So don't let that screw you up. The arm is positive or negative. All the rest of your measurements are not. You're purely working with positive numbers. L, the distance from the main wheels to the nose wheel or to the tail wheel, depending on the aircraft type. Again, it is always positive. It is not an arm. It is purely the distance between the 2 sets of wheels. F is the weight at the nose weighing point, if it's a tricycle gear aircraft. R is the weight of the tail weighing point in a conventional tail dragger aircraft. So if we apply them, here is that first one. So here we have a nose wheel aircraft, datums forward of the main wheel, and I've got what our different variables are. But what we're going to do is perform a quick calculation to figure out what the CG of this aircraft is. And as part of that, we're going to draw a sketch of it because you're going to do this on your lab. So when I say draw a sketch of it, here's the nose wheel. Here's the main wheel. I hear the giggling. Here is the datum. Okay? And we need our, can you guys see that okay? Is that, God, yeah, these boards are ridiculous. We have our, D, so our nose landing gear is 375 pounds. Our main landing gear is 1,050 plus 1025, 1,025, okay, or 2,075, okay? We don't care about left or right at this point because we're only looking fore and aft, okay? Our D, our distance is 120 inches. That's from our nose. You can see nose to mains. Sorry, nose to datum. Okay. Our L, did I draw? Yeah, I drew the datum. I drew something off, I think. That's what I did. That's where a datum falls. Because it's further from one to the other. This is it's different from the picture shown here. I think that's why I did it. Here's the datum. There we go. So it's still in front of the main wheels, no matter where it's at, right? So this is where the distance to the main wheels from the datum, there we go, is 120 inches. And the distance between the two wheels is 115 inches. Okay, that's L. Right, so this is D, this is L, right? And then we have that. Okay, so when I tell you you need to, in the assignment that you're gonna do, where you have to sketch the setup, this is the sketch that I'm looking for. Okay, it's as simple as that. You don't have to draw the rest of the airplane. Just show where the main nose gear is, show where the main gear is, show your distances and where the datum falls. Okay. So then all we got to do is plug those in. So CG equals 120 minus F. What's F? What is it? What's it mean? The nose landing gear weight. Whoops, times L. What's L? Distance between nose and main divided by W, which is what? What's our total weight? Yeah. Total weight is 2,450, right? This plus 375. Right? Okay. What is our CG? What's that? 102 point, we'll just call it 4 inches. And remember, this is an arm, so that's positive. So if I draw that, 102 is going to be somewhere in here. We'll just go down with it here. Like that. Okay? So that's the drawing, that's kind of the sketch that I'm looking for these. Does it match? Yep. Roughly. These are posted on e-learning, so if you want a reminder, if you don't want to have to draw it real quick now. Okay. Okay. If your datum's after the main wheels, you've got a different equation you have to use. I'm not going to go through each one of these, but CG equals negative times D plus F times L over W. Same type of variables, right? So we would plug in for D. In this case, the example I did would be 30 inches. I said the datum's 30 inches behind the mains. F times L, F is the 375 again. You can see I didn't change the weights. But the L, and again, our L, I still kept 115. So it's kind of the same airplane, but I just moved the datum in this case. And if we plug all this one in and we draw a sketch, it looks something like this. So here's our datum on the right behind the main landing gear, 30 inches behind D. The L is still 115 between them. Now you can see when we put it all together, our CG negative 47.6. Remember, because this has that negative in front of it, and these are all positive numbers inside the parentheses, we end up with a negative arm. And that makes sense, right? Our datum's here, our CG typically our CG has to be between our wheels. If you get one of these, if you do the calculations and your CG falls outside of the area between the two wheels, that should be a big red flag. What would happen if the CG was behind the mains on a tricycle gear? Our tail would smash into the ground, right? It would teeter-totter into the ground. These are posted on e-learning exactly like this, if you don't want to. Okay. So if it was in front of the nose landing gear, what would happen? Maybe it would tip up, but probably not tip up, but it'd be really hard to get that nose off the ground. Plane would be going down the runway doing this. Right? Bounce with me, bounce with me. Right? I'm really cool. My kids think so. My 10-year-old won't even, she's like, drop me off way back there, Dad. But I'm going to take you to the front door of your school. No, drop me off back here. What's that? Except that's my wife. I drive the Explorer with the rusty liftgate. She didn't want that. I'm just waiting for truck prices to come back down, but I feel like they're not going to. Okay. If we've got a tailwheel aircraft, we can have our datum in front of the main wheels, probably a very common setup. Okay. But again, the CG should fall between. One of the things I want to actually real quick point out here is if we look at this, you can see I just kind of did another calculation. This was our tailwheel, our tricycle gear. You can see our CG is 17 inches forward of the mains. Same airplane, you can see our CG is again 17.5 inches forward of the mains. Right? So the weights didn't change. All we did was move the datum, worked out the same way. So that's just to show that the datum doesn't really matter where it is as long as you're always using the same spot. When we get into the tailwheel aircraft, these two, where I have an example with the datum in front of the mains as well as behind the mains, they are also the same airplane, just with the datum in two different locations. So if you use my example here, you'll see same numbers, except now our R is the rear wheel for the tail wheel weight. So it's not the exact same airplane, obviously, because it's a tail dragger instead of tricycle. Distance here, I'm putting the datum 5 inches in front of the mains. If that was an arm, what would it have to be? Remember I said these are distances, not arms, so it's not negative. If it was an arm, it would have to be negative. And then our length, 240 here. So if I draw it out, here's my datum, 5 inches in front of the mains. Got my little tail wheel back here, 240 inches away. You can see my CG. I did make a little mistake there, but my CG is 41.7 inches aft of the datum, not of the main landing gear line. That shouldn't have arrows there. I got to go and blank that out. But it's a positive CG of 41.7, again, between the main wheels and the tail wheel in this case. If you have a tail dragger and the CG is in front of the mains, you're probably going to smack your prop into the ground, right? And here is the same aircraft now, but the datum is behind the mains. Okay. And if you were to overlay these on top of one another, use the same weights, the same distances here. The length is the same. I just moved the datum, so that's got a different distance. It's 10 inches now behind the datum, behind the main wheels. If you overlay these, they are basically the same aircraft with the datum in two different locations, and they will end up in the same spot. So, who likes knowing 4 different equations for 4 different aircraft types? You have to learn this method, but it's not my favorite. Here's what I prefer. I like the table method. That's the next thing we got. So the table method, gear type, and datum location are basically irrelevant. But there is a big caveat to this one that students always get screwed up on. That is, you can add the weights together. You can add the moments together. But you can never add the arms together. Stay with me. You can add the weights. You can add the moments. You cannot add the arms. Thank you. Nobody add the arms. I guarantee somebody will. Someone will do it on the homework. Someone will do it on the final exam. Yes, I said final exam. There is one for this class. Yep. We'll show how to do that. Yep. Okay, so you need to know the weights and the weighing points. So again, it could be gear, it could be jack points. It doesn't matter as long as we know what the weights are and how far they are from the datum, the arms. Okay. Arm is the distance from the datum to the waypoint. Again, positive is behind the datum. Negative is ahead of the datum in relation to the aircraft. Okay. So if our datum is at the firewall, what kind of things would be positive? What kind of loads? What? What kind of things specifically would be positive? The what? The cabin, items in the cabin. Huh? Main landing gear probably would be. The flaps would be. What's carried behind the, what kind of things are variable that's carried behind there? The people, the fuel, baggage, okay? This is like a Cessna and that kind of thing. The firewalls on the airplanes I worked on were way at the back. Ours was out in front of the nose. So if we're doing like the Cessna 172 firewall, what kind of things would be negative arms? Engine, prop, oil, right? That kind of thing. So the first thing we do is we're going to take a subtotal as weighed, okay? We just add these up. Remember we said we can add the weights together. That gives us our net weight. We're doing net weight right now, or as weighed. We can add the moments. What's the problem? We don't have any moment. So how do we get the moments? What is a moment? Weight times the arm. So if I multiply these, 377.5 times 5, excuse me, gives me a moment of 1,887.5. Main landing gear left, main landing gear right. You can see they're at the same arm. Okay. Now what can I do? Now I can add my moments together. So this gives me the as weighed moment of the aircraft, 252,088. Okay. How do you think we get an arm? We divide the moment, take that moment, 252,088, and we divide it by 2,462.5, and that gives us a CG in this case of 102.37 inches. Okay? Pretty straightforward, right? As long as you don't what? Don't add the arms. I keep saying this. It's like I have a reason to say it over and over again. How many years have I taught this now? How many years have we had people add the arms? Every year since 2018. Don't weigh the arms. So this is my way of like, hopefully no one will weigh the arms this year. I can finally celebrate if you don't. Okay, now we've got to get our basic empty weight. And in this case, I'm saying I had some chocks that weighed 2.5 pounds. They were at the nose gear, so they're at that 5-inch arm. And I had some main landing gear chocks that weighed 10 pounds, and they were at the 120-inch arm. So we take this, and you can see I made them as negatives, right? Because I'm taking them out. you still are always adding, you're just adding negatives, right? A positive plus a negative works like subtracting. So 2462.5 plus a negative 2.5 plus a negative 10 gives me 2450. Okay. Again, I have to find the moments of my chocks, so I multiply across, and you can see a negative, remember a negative times a positive gives you a negative, right? So again, we can add everything in the moment column to give us our empty moment. And then we take that moment and we divide it by the basic empty weight, and it gives us our basic empty weight arm, also known as the CG. Okay, the aircraft center of gravity. That's a basic empty weight arm. Is known as the CG. Here's another example. In this case, we're going to take out the same basic aircraft, but now we're going to take out the tear before we get to it. So this is another way of doing it. So we can take our weights. We can subtract out the chocks right here, our tear weights. So I've got the tear right here. Here's my 2.5 pound chocks, and I had 5 pound chocks on each main. That's where the 10 came from. You know, in the previous example, it was 2 5 pound chocks. So there's my net weight. You can see that matches. Add my weights together. Multiply my net weights times my arms to get my moments. Add my moments together to get the empty moment. And then what do I do to get the empty arm, the empty CG? Divide the moment by the net weight. Gives the same number, right? Okay. And again, we don't care if this is a tail wheel, a nose wheel. We can take our table and now we can add additional items to it to track modification repair. You can see how this looks a lot like the empty weight calculation in the pilot operating handbook, and now we're adding a modification data to it. So Western over at the engineering college used to have, I don't know if they still do, they had a modified Cessna 172. It was experimental. And what they'd done with it, they used it for the aeronautical engineering program, which Western has a really good aeronautical engineering program. If you think about switching to engineering, it's actually very highly accredited, by the way. But they removed the rear bench seat, and so you would take the weight, and where did I get this weight and arm for my rear bench seat? Where'd that come from? The equipment list. Comprehensive equipment list, very good. That would be in the pilot operating handbook or the aircraft flight manual. Okay? And they installed a test equipment rack. It's experimental. They had to do their own figuring out of that thing, I'm sure. I'm sure they were real precise on it too, based on the operations I saw going on with that airplane. So when I saw them operating it, they were looking at icing. They basically would build like fake ice shapes and attach them to the wing and then go fly the airplane. And they'd have yarn stuck all over it so they could see the yarn lifting up when it started to stall in different areas. Nothing like attaching unknown shapes to your wing and going and flying the airplane and stalling it, right? They just do a little section of the wing, so it only made it a little unsafe. So there's our new updated empty weight. Now this is before they've installed any equipment in their test rack, but they've got a rack there too. And this is back in the day where they had to put like VHS VCRs in there to record the video cameras. And they had to put other, it wasn't like today where you can carry a GoPro in your pocket. So there is our moment. And you can see because we removed the bench seat, negative, we get a negative moment for the bench, positive for the installation. We calculate our new moment by adding the moment column, the right-hand column. And then we divide the moment by the net weight to find our new arm. So you can see what happened to our CG here. We're seeing their gravity move forward. Makes sense, right? We removed a heavier seat from the back and we put in a lightweight aluminum rack. Right? So that meant the center of gravity moved forward a little bit. They would then could do additional calculations to load the airplane for flight. So this is what the pilots do. This is kind of the next step, and they do the exact same thing. So here they've got their different fuel. They add in unusable or take out unusable fuel because we include unusable fuel, right? But then they're going to add back in full fuel, which includes adding that unusable fuel back in. It seems kind of counterintuitive, but they have us keep unusable fuel in, and then the pilots have to subtract it out, and then they add in full fuel, for instance. The pilot, baggage. Oh, now they've added some test equipment in our rack here. Right? Slot in maybe at that time, that 47 pounds is probably like a VCR, and maybe if it was 1980s era, it'd be a VCR, and that'd be it. Okay. So there's the flight load, the full weight. This is where, it's important that we get our empty weight correct, because now they're going to take this plane out and fly, and we don't want to kill anybody. They can figure out their moment, and they can figure out where their new CG is. You can see it's moved back a little bit. That makes sense, because everything they've added here, for the most part, fuel, that's behind the firewall. The pilot is behind the firewall, baggage is behind the firewall, the test equipment, right? That all added to it, so it moved our CG further back. But we want to make sure it's not so far back that the airplane is going to want to do one of these, or that it'll go into a spin and they won't be able to recover. So they take that, and now we have to compare that against something called the CG envelope. Okay. So they're going to have a table that looks like this, which is the loaded weight. And there's two versions. One can be loaded versus the CG, so the CG arm. Or they may, well, so here's our example, sorry. So if they had their loaded weight, in this case, of 2,000 pounds, and our loaded CG, in this case, of 44 pounds, you can see where our star ends up. For them to be okay to take off under normal category, they have to be in this area. Okay? There's our max weight of just shy of 2,300 pounds, 22 something, 2280, I think, or something like that. And then you can see, I mentioned earlier, there's a more restrictive utility category over here where you can have lighter weight, but you can have your CG further forward. Okay. You can also take the loaded weight versus a loaded moment, and that's what's shown here. So instead of weight versus CG, this is weight versus moment. And so if we take the same example, if we have a loaded weight of 2250, moment, now here's that 95 inch, what's the actual moment here? What's that? 95,000. This would be a 95,000 if we didn't divide it by 1,000. Okay. But see how they divide it by 1,000 to make it a more workable, easier to understand number. So you can do it either way for small aircraft. But earlier I mentioned there's a third way. So it falls in the normal category. Here's a version of it. Here's a version of it. 950 pounds, inch pounds over 100, or 95,000 inch pounds. There's the three different versions. These are the two main ways you'll see GA style aircraft. If we're using a bigger aircraft, you'll have to figure out something called MAC, or mean aerodynamic chord. And that's what's shown here. So here is our zero fuel gross weight, okay? And here is our CG percent MAC. And they're doing a zero fuel gross weight. We use this in the airline rather than doing fully loaded weight. Is they would always calculate CG based on zero fuel gross weight, and that meant they could add any amount of fuel. This envelope allowed them to add any amount of fuel. So it didn't matter how long the flight was, we didn't really have to take fuel loading into consideration. It was the zero fuel to full fuel will fall anywhere in here as long as you're good at zero fuel. And then we have our mean aerodynamic chord, percent of mean aerodynamic chord. Show of hands, who knows what mean aerodynamic chord is? That's about what I thought. I never actually figured it out until I came here to teach, and I went back and like, I should really be able to explain what this is. I mean, I knew how to look up the number and how to put it in, but I never So an example here, if we have zero fuel gross weight, so zero fuel gross weight is the empty weight of the plane plus passengers and baggage and all that. It's minus, no fuel. And if it had a CG of 40% Mac, it would fall within the envelope here. So this plane would be good at basically any fuel weight. And I talked about why fuel is not included. We want to be able to use any amount of fuel that we have. Part of the reason we have to do this is because most of your larger aircraft are swept wing. What is the key with a swept wing aircraft and fuel as it's burned during flight? What's that going to result in? What's that? The CG is going to move forward, right? Because the fuel tanks are swept back. So as the fuel burns, it's going to move more and more inboard, which is also more and more forward. So that's why we want to have a CG range that can take into account any fuel weight. Because when we start, maybe those wings are nearly full. And by the time we land, they're nearly empty. And so you don't want the plane to become uncontrollable at some point during that flight. So how do we find the Mac? Here's a wing. We take the wing root length, and we add the wing root length in front of and behind the tip length. So it gives us a total Mac length at the tip. We take our tip length, and we add that in front of and behind the root. Then we draw a line from the front of the inboard or the inboard lines to the aft end of the outboard, the tip line. We take another line and draw it the other way. This gives us our point on the wing where we're going to measure mean aerodynamic chord, because there is not a single chord length on this wing, right? It has a wider chord at the base than it does at the tip. So the mean aerodynamic chord, the average aerodynamic chord of this wing, falls along the line that is at that point where those two lines cross. So this is a very high level intro on it. So that is our point. So that distance, and they, rather than calling it the distance in inches or the distance in millimeters, we just call it a percent of that distance. 50% of that distance is halfway back. 75, 3/4 of the way back. Okay. So here is our max. So if our CG falls here, for example, this would be 25% of mean aerodynamic chord. It's the distance from the leading edge at the mean aerodynamic chord point on the wing. Do you get that all? Distance from the leading edge at the mean aerodynamic chord point on the wing. There's 50% Mac, 75% Mac. And so that mean aerodynamic chord essentially sets your kind of where your lift range is going to be on that wing. And so we want to make sure that as we're flying the airplane, as that CG moves because of fuel burn, it's actually going to move more forward as we travel, right? It's going to start further back, and as we burn fuel, that's more back here. It's going to be heavier forward. It's going to move forward, move forward. We want to make sure that that plane's going to stay controllable, pitch controllable the whole time. You may have to retrim it. Oftentimes you'll trim the pitch trim to make up for those changes, but it's still going to maintain controllability. Okay. That is hopefully everything you need to know for now about weight and balance.